Let's record this so that you can watch it later if you want. The first question I had, I thought this was a good one, was you have these different kinds of lines that you can get in this kind of wave optics thing that you're doing. You can have bright lines or dark lines. Right? And there's different equations for each of them. But how do you know which equation to use and when to use which one? Right? This is a good question. So bright lines, basically you're looking for bright lines anytime they ask you for a maximum in an interference pattern. That's going to be bright lines. And also you're going to see bright lines when you have multiple slits. So if you're going through basically two or more little slices inside of something. So that's how you know you're using bright lines. And then dark lines are going to be if they ask you to find the minima. If you're finding a minima of multiple slits, that's the places where you're getting destructive interference, so you're getting waves canceling out. I believe that's the m plus 1/2 kind of equation. And then the other kind of dark band you can have is predicted in the single slit equation. So in the single slit, you can only find the dark spots. You won't find bright spots for the single slit.
How are we doing today?
No. How are you doing today?
Yeah.
I fixed the whiteboard. It's horrible, so I just used the TV. After this, we'll watch some movies. Actually, we are. We're going to watch a movie club. Yeah. With future me. You're going to see future me. Okay? So any questions on that, bright lines or dark lines? So bright lines, when you have maxima and when you have multiple slits. And then the dark lines, or if they ask you for the minima for multiple slits, or if you're using a single slit. Yes?
How do you know if the order is positive or negative?
Order for when you're actually plugging it in,
Yeah.
always just plug in a positive number. Order number is always positive, and you basically have an m equals 1 that's above, and m equals -1 is below.
Right. Okay.
Another question, Claudia?
I was just trying to figure out what that little thing in between the M and 1/2 was, but it's a plus sign.
Yes, that's a plus. I have horrible handwriting. This is the problem with being a doctor. Doctors have awful handwriting.
Yeah.
Yeah. Any other questions on that? Okay, so let's do a problem. Let's do problem number 14. Somebody want to read problem 14 for us? Or do I need to read it myself? You can read it? Read nice and loud.
Oh. Find the largest wavelength of light falling on double slits separated by 1.2 picometers, for which there is a first order maximum. Is this in the visible part of the spectrum?
Okay. So I think was it picometers?
Is that what they use?
I hope not. No, the little mu is micrometers. Yeah. No, that's fine. That's fine. So this is 1.2 little mu meters. So that's how far apart the slits are. Yep. Which is 1.2 times 10 to the -6 meters. Now we're asking about interference patterns, right? So what kinds of equations relate to interference patterns? What equation are we going to want to use? Multiple slits, it's a maximum. So do we want bright spots or dark spots? Bright spots. And what's the bright spot equation? M times lambda, which is wavelength. And that's equal to d sine of theta. What were we asked to find in this question?
The largest wavelength.
Largest wavelength. So we can solve this equation for wavelength, divide both sides by m. And lambda is d sine theta divided by m. What else did they give us? Did they give us any of these other variables? They gave us d, so we know d. Did they give us sine theta? Is there an angle written anywhere in there? There's no angle written anywhere in there, but they did give it to us in kind of a roundabout way. How about m? Did they give us m? It was the order of the bright spot. First order. Okay, so we know m is equal to 1. So the only thing I need to find now, I need to find this theta. And kind of buried in the reading is where the theta is. So theta, if I draw a double slit, I have my little screen at the back. I have the central bright spot. What's that labeled? The very middle bright spot. That's m equals 0. And then I have the first order. So I have a bright spot up top, and I have another bright spot kind of down below. First order, and I can have a second order, and I can have a third order, and so on and so forth. The angle I draw, that theta, is the angle between a line that goes from your screen to the central bright spot and wherever your first order maximum is. So this would be theta for this particular picture that I've drawn. This is a completely general picture. That's how the double slit works. We get bright spot, and then bright spot, and then bright spot. So now we need to take this and we need to adjust this picture for a bright spot for a maximum wavelength. For maximum wavelength that you can shine through this, you're going to want to put your your very first bright spot at a specific angle. So you want your first order bright spot to be maximally diffracted, bent to the maximum amount. So what is the maximum amount that this light can bend? How far can it go? This might make sense after I actually draw it. Somebody I think might have said it. 90 degrees. So the maximum angle that this can bend is 90. Let's see what that looks like. There's my double slits. There's my wall at the back. There's my central line. And the maximum angle that I can diffract is 90 degrees. That's if I bend exactly upwards. All right, I can't go bigger than 90. What happens if I go bigger than 90? Then I'm just going backwards. I end up behind the wall. So 90 degrees is the biggest angle I can get. So to find the maximum wavelength, I plug in that biggest angle. So I have lambda equals d, which is 1.2 times 10 to the negative 6, times sine of 90 degrees, all divided by 1. Plug all your numbers in, you get 1.2 times 10 to the negative 6 meters. So now we know to find the maximum wavelength, you plug in the angle is going to be 90. Okay. And that will work generally for any. So I can give you different slit sizes, I can give you different orders, but the maximum could be a number. Then they also ask us, is this in the visible range? So what is the visible range of wavelengths? And we remember that from the reading.
380 to 760.
Sure. Visible is about 400 to 700 nanometers. Is this in the visible range? 1.2 times 10 to the negative 6 meters. To know if that's between 400 and 700 nanometers, what do I need to do? Convert that into nanometers. How do I get that into nanometers? 1.2 times 10 to the negative 6 meters. 1 times 10 to the negative 9 meters is equal to 1 nanometer. So I do this conversion, and I get about 1,200 nanometers. So is this in the visible range? No. Could we see this? No. What wavelength range would this be in? What color is 400? Short wavelengths. Violet. What color is 700? Red. So what would 1200 be? What's past red? Beyond red.
Oh yeah.
Further than red.
Is it infrared?
Infrared. So that would be doing it infrared. Okay.
Yeah.
Any questions on problem number 14? Nothing on 14? So that one was tricky because you kind of buried in the reading what the maximum wavelength means to plug in the right angle. Yeah.
So if they said like minimum wavelength, would it be 0?
Minimum wavelength? Yeah. I wouldn't ask that. Okay. All right. The other question that I was asked to solve was question number 38. Do me a favor and let's read 38 for me. Anybody? Go for it again. You're just going to rack up extra credit points for reading.
Okay. He-Knee laser beam?
Yeah, sure.
He-Knee laser beam is reflected from the surface of a CD onto a wall. The brightest spot is the reflected beam at an angle equal to the angle of incidence. However, fringes are also observed. If the wall is 1.5 meters from the CD and the first fringe is at 0.6 meters from the central maximum, what is the spacing of grooves on the CD?
So grooves on a CD basically act like slits. So this is the picture that they're giving us. They're giving us a wall that's 1.5 meters away, and we're getting a first order bright spot right here at 0.6 meters from the middle. Okay. So we're working with bright spots. What's the equation to use for bright spots? M times wavelength is d sine theta. Okay. What are we asked to find? Which variable in that equation am I looking for?
D.
D. How do you know it's D?
Because it said the spacing of the grooves.
What's the spacing of the grooves? The separation of the slits. Okay. So we have to find D. So I should solve this for D, divide both sides by sine of theta. Cancel out my sine of thetas. I get D is m times lambda divided by sine of theta. Okay. Do I know any of these things? Do I know what m is?
0.7.
M is the order of the bright spot. So m is always an integer.
This is the brightest spot.
The bright spot.
The brightest spot.
The brightest fringe spot. So the brightest fringe spot is the first order bright spot. The central bright spot is just the central bright spot, and then these things, another name for them is fringes. Okay. So we have m equals 1. First bright spot. Also call it the brightest fringe. Anybody remember that TV show? Did anybody watch Fringe? Oh, it was a great show. You should all go watch Fringe. Over spring break, that's your homework. How about lambda? Did they give us lambda?
Unless we know what a He-Knee is.
We do. We know what a He-Knee laser is. It's a helium neon laser. The wavelength of a helium-neon laser is 6.33 times 10 to the negative 7 meters. That number is in the reading. So it's in the book. You can also find it in, I think it's example 1 in this chapter, to actually derive that wavelength for. Okay, so on an exam, would I give you that number as a constant? Yeah, you'd be given that. You tentatively say, please? Yeah, I'll give you the wavelength of the laser. You don't have to know the wavelength of the Heaney laser. Okay? So we know the wavelength. We know M. What else? What's the last variable? Theta. Do I know what theta is? People that say yes. I don't see. They didn't give me the wavelength. Or they didn't give me the theta. I don't see a theta in there. Where's theta? Find it with a triangle. So this is my theta. How can I find that? Opposite over adjacent, which is tangent. So theta is the inverse tangent of 0.6 divided by 1.5. Brightest fringe, first bright spot, always one. So I can plug and chug that into my calculator and I get a theta. If I plug and chug that into my calculator, I get a theta of 22. So then we plug all of our numbers in. D equals 1 times 6.33 times 10 to the negative 7 meters, all divided by the sine of 22 degrees. I plug all of this in, and I get D is equal to 1.68 times 10 to the negative 6 meters. So that's how far apart my slits are. Now, if you go back later and you're studying, and you go look in the back of the book gives you a different answer. Back of the book gives you D equals 1.58 times 10 to the negative 6. Which one's right? Who's right, book or me? Who said book? Both? Yeah, both are right. So I didn't round, the book rounded. So the rounding can affect your answers a decent amount. Any questions on number 38? Okay.